So I was looking for some vanilla in Albertson's supermarket a couple of days ago, and I thought it'd be very easy to just go grab a bottle of vanilla extract. I wasn't aware that how different the prices are between actual real vanilla extract and the imitation vanilla flavor stuff. It's not obvious to me why 1 ounce of the natural stuff should cost $6, whereas 8 ounces of imitation vanilla flavor should cost only $3. That's a huge price differential. Deep down inside, I know they just take a vanilla bean and put it in alcohol, whereas here they take the actual vanilla flavored compound and put a few drops in alcohol. And there's not that big of a difference except for these subtle nuances that get extracted out of a vanilla bean, and I'm not sure I can tell those differences. Everything in here is natural, actually, even though, well, maybe except for the vanilla molecule itself. Okay, so let's. So I went to go online and find out what's known about vanilla extracts and what else is in these. What else is in these bottles? And I ran across this really interesting article about the FDA warning people about the kinds of cheap vanilla that you might sometimes find produced in Mexico. And what they warn you against is that sometimes when you go buy, and not in every case, and not this supermarket brand I just showed you, but there have been cases where you go to buy vanilla extract that's labeled as natural, Extracto de Vanilla or something like that, and they warn you that it's not actually vanilla. What they say is that these are actually Tonka bean extracts that contain the compound Coumarin. And I was immediately interested in that. Vanilla is not quite as interesting. Coumarin is very interesting. And so how can it be that they're selling these, selling extracts of a plant I'd never heard of that contain the compound Coumarin? So let's talk about that. What I quickly realized is that if you can find these extracts of Tonka beans, that's actually phenomenal. I want to get my hands on some of this because it turns out that all of the avant-garde chefs out there are using Tonka beans. And it turns out that they are illegal. It is no longer allowed by the FDA for you to use Tonka beans as flavoring. But if you're an avant-garde chef that's trying to impress people, you would use shavings of this, just very subtle shavings of these Tonka beans to try to add superb flavors. And it turns out that these taste very much like vanilla. And the French have known this for a long time. And again, in this article, it reinforces this idea that Tonka beans are a major source of coumarin. So the author of this article, I was pretty impressed by their chemical sophistication. Yes?
Why did the FDA make that illegal?
Because coumarin at high concentrations can be toxic. And I'll address that. Okay, so, and what this author was clever enough to point out is that you would have to eat completely insane amounts, right? Normally you just shave off a little bit of the bean. You would have to literally swallow many handfuls of these beans in order to have any toxic effects. But let's go ahead and take a look at the molecules that underlie this. Like, what is inside a vanilla bean and what do you find inside of a Tonka bean? So if I take a vanilla bean off a tree and I let that thing dry out, the reason why that smells so fantastic in your baked foods or has this wonderful vanilla smell and flavor to it is because of this molecule called vanillin. So this molecule represents about 2% of the vanilla bean. So if you put that into alcohol, vanillin gets extracted in there and has this wonderful flavor. If you take a Tonka bean, different plant, different tree, different everything. If you put these in alcohol and let them soak, you don't soak out vanillin. I don't know if that's even present in these Tonka beans. What you're soaking out is a completely different molecule called coumarin that has these wonderful smells that are like vanilla. And again, this is about 2% of the Tonka beans that gets extracted out. So I'm not so sure I'm comfortable ingesting that on purpose, but I'm dying to do it for whatever reason. And I went and looked up the LD50s. It turns out for every compound you can look up the lethal dose. What's the dosage at which 50% of the animals who take it die? Of course, they've never measured these for humans. You can't subject humans to that. But they know the numbers for mouse. You have to subject yourself to about, at least if you're a rat, to about a fourth of a gram for every kilo of rat or mouse weight. In other words, I'm a 70-kilogram person. You can imagine I would have to take a spoon and eat spoonfuls of pure coumarin before it started to have those kinds of toxic effects. Vanillin is also toxic, right? Everything is toxic if you go to a high enough concentration. Sand is toxic if you go to a high enough concentration, and that's significantly less toxic. It's about 5 times less toxic than coumarin. So you can't claim that vanillin is non-toxic. So you have to be careful about what you say about toxicity. So I'd love to get my hands on some Tonka beans. It's fascinating. There are many natural products and pharmaceuticals that have coumarin type structures in them, and we're not going to talk about those in this chapter, but it's fascinating that that the FDA has decided to make that illegal. It doesn't look that bad to me, and the big time chefs are using that. Okay, so now let's go ahead and go back to chapter 12 stuff. And we're undergoing a major shift in gears. Let me mention that the exams that you took last Friday, those have now been scanned in. I received the files yesterday and I immediately uploaded them to EEE Dropbox. So you can now go to the EEE website and then go to Dropbox. And somewhere on there, I can't look at I don't know what you see when you log into EEE, but you'll be able to click on the file and bring up the PDF version of your scanned in exam. You'll never see your original exam again. But there's a good quality scan in there. So if you have questions about the grading, if you feel there was a mistake in the grading, you can email me. There are instructions on there. We've already given partial credit. Do not send me emails fishing for extra points because we've already given you partial credit for the points. But if you think something was misgraded, then let me know. And again, there are instructions when you look at your exam. Okay, so chapter 12, what did we finish already? So we've covered chapters 9, 10, and 11. So chapter 9, remember, was alcohols. A bunch of SN1 and SN2 and E1 and E2 reactions of alcohols. In chapter 10, we talked about alkenes and all these different reagents you can add to alkenes, like HBr, Br2, Cl2. And we just finished chapter 11, which is basically the same reagents, except we applied them to alkynes. And the one trick we learned in chapter 11 is you can deprotonate alkynes to make carbon nucleophiles. So in this chapter, we're going to talk about oxidation and reduction reactions. These are essential functional group transformations for organic synthesis. And you'll be using these types of reactions through the very end of the Chem 51 series. I can't say the same for SN1 and SN2 and E1 and E2 reactions, but these are reactions that tend to be very useful. So I'm going to give you a definition that's not a perfect definition. This is a functional definition that's probably the most useful to you. So this is the most useful definition I can give you, certainly for this chapter and for the Chem 51 series. And that is that we consider the reduction of an organic molecule to correlate with the formation or the presence of more CH bonds. Now, I'm sure you guys did reduction, oxidation, and balancing equations. We don't do anything like that in organic chemistry. That kind of stuff you did in freshman chemistry. Let me go ahead and draw out a series of molecules so you can see more clearly this pattern of oxidation and reduction. So here I'll draw out a series of molecules, and as I draw these molecules out, I'll keep drawing out molecules that are consistently more oxidized. So here's a molecule where I stick an oxygen atom in there. And so the only difference now is that I have more oxygen-carbon bonds. More oxygen-carbon bonds means more oxidized. More carbon-hydrogen bonds means more reduced. So this compound with the new oxygen-carbon bond here I would consider to be oxidized relative to the first molecule. I can draw another molecule here, an aldehyde. Now I have 2 oxygen-carbon bonds. That's even more oxidized than the alcohol. So if I show you, oh, here's an alcohol, what reagent do you need to use to convert that to an aldehyde? You need a reagent that does oxidations. That's why it's useful to distinguish the oxidation state of these. And let me go to the highest typical oxidation state for organic molecules, and that's a carboxylic acid. So now I have 3 oxygen-carbon bonds in the carboxylic acid. So you can see there's this pattern of oxidation. Let me use a pen here to color that in. As I've drawn this series here going in this direction, that's oxidation. Things are becoming more oxidized. And we'll give you reagents for doing those transformations. Not this first one. We're going to have to wait until the chapter on radicals. I think that's chapter 15, where we'll show you how to do that first transformation. But we'll show you how to transform alcohols into aldehydes and aldehydes into carboxylic acids in this chapter. So the reverse of this process would be reduction. And going in this other direction, those are all require reductive processes. They would all require reductive reagents, reducing reagents, and we'll show you some of those. Probably the most useful reactions will involve transformation of alcohols into aldehydes and back, and we're only going to show you half of that during this chapter. Okay, so let's talk about all carbon compounds that have no oxygen in them, because we can draw a similar sort of sequence or similar sort of pattern. So here I'm just going to draw a simple alkane, and it doesn't matter that it's at the end of an alkyl chain. I just want to contrast this with a CC single bond with a very similar molecule that has a CC double bond. The important point here is even with the same number of carbons, because I have more carbon-carbon bonds in this double bond molecule, that's considered to be more oxidized. Right here, there's a single carbon-carbon bond. Now there's two carbon-carbon bonds. So the alkene is more oxidized. And the molecule that has more hydrogens on carbon is more reduced. And I think you can see where this is heading. If I draw an alkyne, that's even more considered to be more oxidized than either of these other two. So again, there's this pattern that as we reduce the number of CH bonds, those are becoming more oxidized. And as we increase the number of CC bonds, it's becoming more oxidized. And the reverse, I don't know if you call this the converse, is true. As you increase the number of CH bonds, this involves some sort of reduction. Maybe I should have said reduction up above. Let me change my verbiage here to say reduction. Okay, so oxidation in this direction, reduction in the opposite direction. And knowing those patterns, yes?
So does oxidation refer solely to carbon and oxygen bonds?
No, so the question is, does oxidation refer only to carbon and oxygen bonds? It could also refer to carbon and chlorine bonds, but we're not going to show you reagents in this chapter that do that. Yeah, and again, that's the chapter on radicals where we'll show you that stuff. So don't worry about that. Just worry about carbon and oxygen for now, and carbon-carbon. That's really the meat of organic chemistry right there. That's where we need to focus our attention. Okay, so the book starts off with a really powerful set of reducing agents. So right here in chapter 12.2, and it's wonderful that they show you these right out of the gate. I feel like these are among the most useful reagents in this chapter, but they never show you how to use them. It kills me. Oh. So I'm just going to show you, I'll give you a preview of what these reagents are for. It's sodium borohydride and lithium aluminum hydride. And the other IUPAC type name for those is tetrahydridoborate and tetrahydridoaluminate. So here's what you won't see. It's not until chapter 20 that we're going to show you this top secret reaction. They don't show you this yet because your head will explode, but I'm willing to risk that. So here's lithium aluminum hydride, lithium tetrahydridoaluminate. And again, you don't need to know this. I'm just hoping you'll store that back in your brain somewhere. And then when chapter 20 comes along, you are going to be all over that stuff. And then you always follow these reactions up with an H2O workup. Book doesn't always write the word workup, but I do. And before you do the H2O workup, what you've done is you've stapled a hydrido group, a carbon-hydrogen bond, right there where the carbonyl used to be. See that CH bond? That's what that lithium aluminum hydride does. And this is among the most important reactions that you will learn in Chem 51C. So the book shows you the reagents, but they don't show you what you're going to do with them. I don't know why that is. And look at that. After you dump a bunch of water on there, you protonate the alcohol, and you've reduced the carbonyl to an alcohol. That's a reduction process. That just feels so good to see that. And why is that so good? Because you know a zillion reactions you can do with alcohols, right? Isn't it? And once you know how to convert a carbonyl into alcohols, there's now 1,000 things that you can do with that in terms of chemical reactions and further transformations. So the book won't show you that yet. And just to give you a further heads up so that you're totally ready to kick butt when you get into Chem 51C, here's the mechanism for a hydrido reagent. The book will show you an SN2 type reaction an utterly pathetic SN2 type reaction. So here's that hydridoaluminate. 4 bonds to aluminum. That should look weird to you. This whole aluminum thing should look weird to you. And so if you have this tetrahydridoaluminate species, and the negative charge on aluminum tells me that all the bonds to aluminum are nucleophilic, so I shouldn't be at all surprised that it's going to do this. And there we go. That's what's going on here. So, big point here is, remember this reagent, tetrahydridoaluminate? Hold on to it till chapter 20, and 21, and 22, and 23, and 24. You're going to be using that over and over and over again. Very powerful stuff. But I'm never going to ask you this reaction because the book doesn't show it in this chapter. Okay, so that's one type of reducing agent. Let's look at some other types of reducing agents. The ones that they do show you in this chapter, ones that they ask you questions about in this chapter, and ones that I'll ask you questions about. Okay, another type of reducing agent is hydrogen gas. If I want to increase the number of carbon-hydrogen bonds, it kind of makes sense that hydrogen gas might be a reagent for doing that. So let me go ahead and show you a transformation. Here's an alkene. And if I add hydrogen to this, hydrogen gas, you just stir things in a little flask under an atmosphere of hydrogen gas, and the product no longer has a double bond. Maybe that's what a naive person might see is, oh, the CC double bond is gone. Here's what I see. What I see is 2 new carbon-hydrogen bonds. That's what I see, even though they're not drawn for you. That's what I see there. So it's not just that the CC double bond is missing, it's that there's 2 new CH bonds. And those both came from the hydrogen. Now, if you take an alkene and you mix it with hydrogen gas, nothing will happen on the time scale of your undergraduate career. You have to add a catalyst to this, and I'll tell you about those catalysts. Secret catalysts. They're too secret for me to show you right now, but I'll show you in just a little bit. There's actually lots of catalysts that will do these. We'll talk about that shortly. Okay, that's one type of reducing agent, hydrogen gas. Very useful reducing CC double bonds. Let me show you another type of reducing agent that's completely different.
So the H2 catalyst, it only is for double bonds, it's not for single or triple bonds?
I'll get to that later. The question was, can you use this for triple bonds, the hydrogenation? I'll talk about that later. Okay, so if you want to reduce an alkyne, one of the double bonds in an alkyne, we have a reagent that can do that, a reagent combination that's very different from this hydrogen. And it looks like this. It's sodium, and I'm going to show you the stoichiometry. You have to use 2 sodiums to make this work. And sometimes I put the little 0 here to indicate that it's in a 0 oxidation state. Sometimes I leave that off. The important part is it's not 2 sodium plus cations. 2 sodium plus cations wouldn't do anything. Those are not oxidizing agents. The reason this works is because sodium metal wants to be a sodium cation. And there's one and only one solvent you can use for this, and that's ammonia. You have to have tons of excess ammonia there, because that ammonia is the source of these 2 new H's that get added there. Okay, and we'll talk about that shortly. So here's 2 types of reducing agents we're showing you, and we're going to use those throughout this chapter over and over and over again. Hydrogen gas and sodium and liquid ammonia. And unfortunately, we're not really going to use that lithium aluminum hydride except for an SN2 reaction, and that kills me. Okay. Let's talk about this hydrogenation. That's what we call it. Hydrogenation is the addition of hydrogen across a pi bond. So our secret catalyst that we're going to use for that hydrogenation reaction is palladium on carbon. And first let me draw that out, and then I'll explain to you what that is. So let me draw a molecule with an alkene. Here's my molecule with an alkene. Here I'll draw my reagent. Usually I draw it above the arrow, but in this case I'll just draw it side by side next to my alkene. So you can see that those 2 hydrogens are going to add across that C double bond. And then the catalyst that we use for this, we write like this. We write palladium on carbon. And I like to write the word catalytic there. I always like to keep straight which things are catalysts and which things are stoichiometric reagents. You don't have to do that. The book doesn't do that. At least it doesn't always do that. But I like to do that. I like to always keep straight in my mind what's the reagent versus what's the catalyst. Because the reagent ends up getting incorporated in the molecule some way. Okay, so the product of this reaction looks like this. And what's the important feature of what just happened here? It's not that the two methyls went down. It's that the two hydrogens got added from the same face. In other words, this reaction involves a syn addition of hydrogen atoms. It involves a syn addition. So because the two hydrogens got added from one face, the two methyls both have to be going in the opposite direction. This is a meso compound. So if I draw the mirror image is identical. So if I put the two methyls going up and the two hydrogens going down, that's the same molecule because it's meso. So don't worry, I purposely chose this because I knew it would give an achiral molecule, a meso molecule. Okay, so what is this palladium on carbon? If you just take charcoal and you grind it up, just take some charcoal and grind it up, you'll have teeny tiny little particles with massive surface area. And so here I've got this picture drawn of a carbon particle. I took this off the web. You can see it's pitted. There's massive surface area in there. It's not just like a square block. And all that surface area provides sites for chemical reactions. Some very clever person figured out that you could deposit palladium all over these immense surfaces of each carbon particle. And that's what you use for hydrogenation. There's so much surface area. Everything is occurring on the surface of palladium. And the carbon underneath is not really consequential. It's just a high surface area particle. What's essential is that it's palladium that's acting as the catalyst in this reaction. We will never talk about the mechanism for this reaction. Don't worry about the mechanism for catalytic hydrogenation by palladium. You don't need to know that. Okay, so let's go ahead and talk about a different kind of substrate where we will, right, not every case gives you a meso product. So let me draw a type of substrate here that would not give you a meso product. I'll just put a single oxygen atom in that substrate, and I'll remove one of the two methyl groups. And so now when I add hydrogen across this, it's not going to give me a meso product. And this will give you a chance to see how I would typically draw out my reagents. I put reagents above the arrow, and I put solvents below the arrow. So typically I would write my reagent hydrogen above the arrow, and I would write catalytic palladium on carbon. And again, the book won't write catalytic, but I do that. Hope you do that, but I wouldn't count you wrong if you didn't. Okay, so there's two different faces of this olefin. So let me go ahead and try to help you imagine edge on what you would see if you were looking at the two faces of that olefin. I'm going to try to draw this kind of fancy edge on version here. And here's my bonds going in back. And then I have these bonds going forward, and there's a CH3 group. This is what I would see, something like this. The point is, if I were to look at that substrate edge on, there's two different faces to that CC double bond. And so the hydrogen gas can add from either the top face or the bottom face. And so you will get both products out of this reaction. You'd get a pair of enantiomers. You'd get the product where the hydrogen added from the top face, and you'd get the enantiomer where the hydrogen added from the bottom face. And I'm not going to draw, whoop, that should be, here I'll just write CH3 there. So I'm not going to draw the other hydrogen. Yes, there's another hydrogen that got added, but the hydrogen that got added to this bottom carbon, it doesn't create a stereogenic center, so I don't want to focus on that. Okay, so just important to remember that when you hydrogenate, and there's two faces to a double bond, you'll hydrogenate on both faces. And you have to note the stereochemical consequences of that. We ask you on the exams, clearly indicate stereochemistry in the presence of stereoisomers at the front page of our exams. And this is an example of, well, where you will have to pay attention to those stereoisomers, the potential formation of stereoisomers. Okay, so two faces, top and bottom face, where you can add H2. Just remember, and I think after chapters especially after chapter 10. You ought to be good at thinking about addition to top and bottom faces of double bonds. Okay, let's talk about some, I'm not sure if it's a limitation, but some things that you need to remember about hydrogenation. And the first thing that I want to emphasize is the unique lack of reactivity of the double bonds in a benzene ring. And I asked a question on the last exam where I had a halogen on the benzene ring, and you were supposed to recognize that, oh no, halogens, chlorine or bromine on benzene rings never react. They never do SN2 or SN1 or E2. And some people made a mistake of trying to do stuff with halogens on benzene rings. Those don't do any of these SN2 or SN1 type reactions. The double bonds in a benzene ring also don't hydrogenate. Under any conditions that we show you, those double bonds are unreactive to hydrogenation. So in other words, if I take this molecule and I treat this with hydrogen and catalytic palladium on carbon, then the only double bond that's going to get reduced here, that will be reduced, is the double bond that's sticking off of the benzene ring. The three double bonds inside the benzene ring, they just laugh at the reagent. Double bonds in benzene rings are super happy. If you want double bonds in benzene rings to react with something, you need super duper powerful electrophiles, and we will show you those electrophiles in chapter 18, but we're not going to show you those super reactive reagents until then. So as far as you know, nothing reacts with the double bonds of a benzene ring. And you have to wait till chapter 18 to see anything different about that. Okay, there's one more issue I want you to look out for, and that is carbonyl groups. So I'm using pH as an abbreviation for a phenyl group or a benzene ring. Remember, the double bonds in a phenyl group don't react with hydrogenation conditions. So if I treat this with hydrogen gas and catalytic palladium on carbon, then we'll end up adding two H's across that, and I'm not going to draw the H's here, but I've added two H's now across that double bond, the CC double bond. This is the main product that you'll get out of this reaction, but you'll also get an additional product. Under certain conditions, and this is not a reliable reaction, you will reduce carbonyl groups down to alcohols. And it's not very efficient. I don't want you to try to use hydrogenation of carbonyls. So in other words, I'll draw this H in, I'll use this sort of thinner pen here so you can see. In other words, in addition to addition of hydrogen gas across the CC double bond, you're also going to start to see some addition of hydrogen gas across the CO double bond. And that's not as easy. It's not reliable. You can't reliably use that, and that's why I don't want you to use it in a synthesis, because you cannot possibly predict when that's going to be efficient or not, so I don't want you to use that reaction. So you have to be careful if there's carbonyl groups in your molecule, because those might get reduced by hydrogen and palladium on carbon. I'm only addressing this because the book mentions this, and I wish they hadn't mentioned it. Our lives would have been so much easier, because almost always it's possible to carry out selective hydrogenations, but now that the book has brought that up, I'm letting you in on the capriciousness of carbonyl reduction by hydrogenation. Okay, so benzene rings, don't hydrogenate them. Don't worry about those. Those double bonds are super happy and super stable. Carbonyl groups, be careful when you draw out hydrogenation. I'm going to be super careful when I ask you questions. I'll be super careful when I ask you questions because I know you can't predict when carbonyls reduce. When I choose my questions for the exams and the problem sets, we're going to be super careful about which questions we ask you so that we don't put you in a position to try to decide whether a carbonyl is going to be reduced. Okay, so CC double bonds, hydrogenation. Let's talk about triple bonds. And I'm going to show you two different recipes for hydrogenating triple bonds. And let's go ahead and start off with this secret catalyst here, Lindlar catalyst. You could also say Lindlar's catalyst. That just sounds weird to me, though. Okay, so here's our reaction. If we take this alkyne here, and we add, I feel like my pen is running out of steam, so I may have to start double drawing on these. So if we add hydrogen gas to this, and instead of writing catalytic palladium on carbon, I'm going to write Lindlar catalyst. And this is the way I expect you to write it. Catalyst. I suppose if you wrote cat period, I would know that's the abbreviation. I'm not going to write catalytic Lindlar catalyst. That's kind of redundant. I'll just write Lindlar catalyst. What is Lindlar catalyst? It's actually a type of palladium catalyst. Somebody found that if you dump in some extra ingredients when you're coating little particles, it's not carbon particles, but basically seashell, calcium carbonate particles. Somebody found when you dump in quinoline and barium salts and other stuff that you can deactivate partially the Lindlar catalyst so that it no longer is capable of reducing simple CC double bonds. So this Lindlar catalyst can't reduce CC double bonds. Look at that, it's still there in the product. But it can reduce triple bonds. And moreover, it reduces triple bonds so that you get a syn addition of hydrogen, so that the two hydrogens end up on the same side. So if you want to generate a cis double bond, then you use this Lindlar catalyst. And I will show you another reducing agent that gives you the trans double bond. So see how important this is? Because Lindlar catalyst can't reduce double bonds, it stops at the CC double bond. And it never touches this other CC double bond in there. That doesn't react. So Lindlar catalyst is special for that. Okay, don't worry about the structure of Lindlar catalyst. I will never ask you that. Yeah, just if it bugs you, you can just remember it's a special type of palladium on particles. All you have to do is write Lindlar catalyst. Okay, what happens if you take hydrogen and regular palladium on carbon? Because you're going to have a hard time keeping these straight. This is going to seem like the hardest thing in the world for you. It's like, what, hydrogen, palladium on carbon, or Lindlar? I can't remember those two. Yes, you can remember those two. You'll be able to do it. But it's going to be very confusing at first. All you'll see is the hydrogen gas, and that's the same reagent for Lindlar catalyst and palladium on carbon. Let me show you what happens if you take an alkyne and you treat that with hydrogen and palladium on carbon. So, and the alcohol doesn't matter here. I'm just trying to make an interesting substrate. So I'm going to be very clear here. What happens if I add 2 equivalents of hydrogen gas and I throw in catalytic palladium on carbon? Two equivalents of hydrogen gas. You'll burn that triple bond all the way down to an alkane. And there's nothing to worry about, does it add syn or anti, because you'll end up with this rotatable bond. You won't have any stereocenters there because you're adding 2 hydrogens to each carbon. And just in case you can't see, here's those 2 hydrogens. Here's one pair of hydrogens right there. And then there's another pair of hydrogens on the same, there's the hydrogens. So if you'd like to convert an alkyne into an alkane, this is a great way to do it. You just add 2 equivalents of hydrogen or excess hydrogen and catalytic palladium on carbon. This is going to kill you because in the back of the book, in the back of the chapter, they're going to have all kinds of questions where they ask you how to make this, and you'll be, what? I don't know how to make carbon-carbon bonds like that. Well, you do know how to make carbon-carbon bonds like these. You know how to make carbon-carbon bonds like that. And you know how to make carbon-carbon bonds like that. You take sodium amide, you deprotonate an alkyne, and then you add some sort of alkyl halide and do an SN2 reaction. So you know how to make those, and once I'll just write know how to make. So you already know how to make these kinds of bonds. Once you hydrogenate those down, nobody can tell which bonds you made. It hides, it sort of masks which bonds you actually made when you synthesize this molecule. That's going to make it very difficult for you to do retrosynthetic analysis and figure out, gee, how would I synthesize that? So that hydrogenation makes the triple bond disappear. And it sort of will hide these potential CC bond forming reactions from you. Okay, so frequently you're going to be asked, like on a problem set or on an exam, how would you do the following transformation? How would you do this? And you won't be able to remember Lindlar catalyst. You'll be like, well, it's hydrogen and some hydrogen and something, and I can't remember what. All I can remember is palladium on carbon. And what happened? Maybe I could just use one equivalent. I know, I'll just throw in one equivalent of hydrogen, and that'll solve. That's not going to work. You have to remember Lindlar catalyst to make this work. Here's what happens if you put catalytic palladium on carbon and you don't put Lindlar catalyst. If you don't put Lindlar catalyst here, the problem is that midway through your reaction, yes, the catalytic palladium on carbon will start to do this hydrogenation. But midway through the reaction, the palladium on carbon will see, oh, look, there's more substrates, and it will start to further reduce this as fast or faster than it's reducing the alkyne. So it will start to further reduce this all the way down to the alkane. But now you're going to run out of hydrogen gas because you only put in two equivalents. Or sorry, you only put in one equivalent of the hydrogen gas. And if you don't put in enough hydrogen gas, then you're going to have leftover alkyne starting material. So this is what happens if you throw in just one equivalent of hydrogen. It won't allow you to efficiently make the alkene. There's one and only one way to make that cis alkene, and that's using Lindlar catalyst. So you have to remember those two catalysts for hydrogenation of triple bonds and double bonds. So hydrogen gas reduces all CC double and triple bonds, whereas Lindlar catalyst only reduces triple bonds, only hydrogenates triple bonds. Okay, so what if you don't want a cis alkene? I'll show you another reagent combination that you can use to get the trans alkene. Half the time you want the cis alkene, the other half of the time you want the trans alkene. And so let's go ahead and take an example of that. And I'm going to try to draw some super fancy looking substrate here because I'm bored with just drawing the same alkynes. The important point here is I have a substrate that is an alkene in here. And I'm going to show you a set of conditions that doesn't touch regular alkenes, just like Lindlar catalyst doesn't touch regular alkenes. This is a reagent combination that only hydrogenates alkynes. And you don't have to, the book doesn't draw the stoichiometry for the sodium, but it takes two atoms of sodium metal for every triple bond that you hydrogenate. And it's weird because I'm saying hydrogenation, but there's no hydrogen gas in here. Usually I say reduction. The important point is we're going to add two hydrogens across that triple bond, and it will reliably give us the trans double bond. So this double bond over here on the left-hand side doesn't get touched, but this triple bond is now a trans double bond. And here's the two hydrogens that we just added. There's one, and there's two. So if you want the cis double bond, you use hydrogen and Lindlar catalyst. If you want the trans double bond, use sodium and ammonia. And alkenes don't react. It stops once you get to the alkene. It won't touch this alkene further. It never touches the original alkene. Now, there's going to be a problem here, and I promise you this will be a problem. And that is that sodium and liquid ammonia, this is actually the solvent for the reaction. You know, normally ammonia is a gas. So when you run these reactions, you have to haul this huge tank of ammonia over, and then you take this cold -80-degree dry ice bath, and you blow ammonia gas in, and it starts to condense to make this basically to make liquid ammonia as your solvent. So here's the problem, that this looks so much like sodium amide. You already know what sodium amide would do with this alkyne. If I take this alkyne here and I treat this, so here's a reaction that we learned in the last chapter. If I take an alkyne and I treat that with sodium amide, that's going to deprotonate that to make a nucleophile that I can use for SN2 reactions. let me draw that lone pair there and a minus charge, and here's sodium cation floating around. Sodium in liquid ammonia looks very similar, especially because the book frequently draws it as sodium/ammonia. I see a sodium atom, I see a nitrogen atom, I see some H's. Right? It looks so similar. So you have to keep these straight. Of course, when I draw it, I always draw the sodium as a reagent above the arrow and the ammonia as a solvent, because it is the solvent for this reaction. So you have to work very hard to keep these straight. So remember, I just told you what happens with sodium in ammonia, and the book won't always write the number 2, the stoichiometry 2, next to the sodium, even though that's required. Remember, this gives you the trans addition of H's, but of course on the end, it doesn't really matter that the 2 H's end up trans because there's 2 H's on there already. So you could get the same product here if you use hydrogen and Lindlar catalysts, since there's no existence of cis and trans isomers for that terminal double bond. So struggle to keep these straight. Sodium in liquid ammonia is completely different from sodium amide. Okay, let's talk about the mechanism for this reaction. Yeah?
Why are the alkenes unreactive?
You don't need to know that. It's related to the stability of the CC triple bond and the HOMO and LUMO levels. And it's not worth knowing. Sorry, the question is why are the CC double bonds not reactive? It's not worth knowing. Yes?
Can we get the slide? So if the sodium amide protonates it, doesn't it become the ammonia? So does the reaction go to the right after or to the left first?
Could you say that again?
So the sodium amide to the left
Yep.
reaction, since that protonates it, that becomes ammonia. So don't we have the materials for the reaction on the right?
So the question is, when the sodium amide pulls that proton off, it becomes ammonia. And so doesn't that do this? And the answer is no, because at no point do we have metallic sodium. Let me come back and draw that little 0 here to make it clear that this is sodium metal. And if in the lab, if you've used sodium metal, you know it's nothing like, it's this silver soft metal, whereas sodium cations are like sodium chloride table salt, right? That's sodium plus. At no point in time in this reaction is there ever metallic sodium floating around in here. Okay, let me go ahead and hold off on this mechanism thing, but I want to clarify one issue that has come up on the last problem set. So let me take this time, instead of giving you anything new, to try to clarify something that came up already. And it has to do with something from the last chapter, so I'll write from chapter 11. And it has to do with dehydrohalogenations. I'm sorry, my pen is running out of steam here. Of terminal to give terminal alkynes. So when you have a system that looks like this, and you treat this with 2 equivalents of sodium amide, what happens typically under these conditions is, as you generate the product, which is an alkyne, because sodium amide is also a reagent for deprotonation of this, you're going to have problems that the sodium, and maybe I was lucky or very clever, I never talked about terminal alkynes, I showed an internal alkyne. But when you apply this double elimination reaction to make a terminal alkyne, you have to worry that the sodium amide can come back in and deprotonate this terminal alkyne. And that's going to chew up one of your equivalents of your sodium amide, so you won't have enough left over to do the double reduction. So if you really want to do this, if you really want to effectively convert this into this alkyne, what you need to do is this. You need to take that alkyl halide, dihalide, and throw in 3 equivalents of sodium amide. 2 equivalents will do the double elimination, and the 3rd equivalent will purposely form this acetylide anion, and then you have to add water to protonate that. And there were some problems, I think, on the sapling about this, where that relate to this. If you want, you could also use this for an SN2 reaction. So I'll just write that there. So I never talked about terminal alkynes in this double elimination process in lecture. So again, if you want to do double elimination to make a terminal alkyne, you need to throw in 3 equivalents of sodium amide and then protonate the product in the end. And that also gives you the option of using that terminal that acetylide anion. Okay, when we come back on Monday, we'll talk about the mechanism for this dissolving metal reduction, and then we'll launch right into some other types of, I think, oxidation reactions that'll become really essential.